Stimulated Reservoir Volume, SRV, and Trilinear Numerical Models. When analyzing an unconventional reservoir with strong nonlinear effects, the most rigorous option is to run a numerical model. With longer laterals and more fracture stages, the corresponding numerical models require a high number of grid blocks, and they can become very CPU intensive. Even if a single model runs in minutes, history matching iterations could take significant time. With certain assumptions about well geometry, the problem is reduced to the element of symmetry. All the nonlinear effects are correctly captured in this case. Let us consider the simplest well geometry, multiple identical fractures that are vertical and orthogonal to the horizontal wellbore. At an early stage, it is reasonable to assume that there is no contribution coming from the outer reservoir. This is represented by rectangular boundaries around the well. Due to the system symmetry, the individual fracture influence zone is contained within the area between the effective no-flow boundaries at half the distance between the fractures. A single repetitive element is considered. Every element like this behaves in the same way. So instead of modeling the entire well, we can model this element and then multiply the resulting rate by 4 times the number of fractures. The same logic applies if some contribution from the outer reservoir is considered. Assuming the outer reservoir flows into the well, we arrive at a trilinear model. This model considers 3 consecutive linear flow periods: the flow through the fractures, the flow towards the fracture from in between them, and the flow from the outer reservoir. Again, a symmetry element can replace the full well model. In both SRVB and trilinear geometry assumptions, the grid representation is very simple for the repetitive elements. A detailed numerical solution is found very fast for complex cases accounting for any of the following nonlinearities: multiphase PVT with relative permeabilities and capillary pressures, pressure-dependent permeability, and porosity relationships. Let us look at data from an unconventional well. Select Fractured Horizontal and SRVB Bounded for the analysis tools. The reservoir and boundary model fields are empty, as these are included in the model assumptions. When this model is selected, and after extraction, the diagnostic lines are added to the log-log plot. By default, the lines are automatically matched to data. The straight lines correspond to the infinite acting radial flow, SRV flow, and linear flow. The horizontal stabilization should be placed beyond the data. Its lowest position above the data can only give a highest estimate of reservoir permeability. If any of the well parameters are known, such as well length, they can be input in the parameters dialog and unticked for the values to be kept. The other lines are adjusted to match the data. Create an analysis copy named SRVB. For a highly nonlinear case, go directly to a numerical model and select Reset from Diagnostic. The infinite conductivity fracture model can give unrealistic high values at the beginning, so it is good practice to impose rate constraints. Define 10 million standard cubic feet per day as the maximum surface rate constraint. Check Keep Dialog Open and Generate. To make the model run even faster, an option can be used that runs with a 5% approximation. This will considerably speed up the simulation without precision loss. Run the model again. Then select Improve and choose the key variables to find a match. Fracture half-length and reservoir permeability in this case. As individual models run very quickly, the match is found in seconds. Create an analysis copy named Trilinear. Go to Numerical Model and change modeling type from SRVB to Trilinear. For the Trilinear model, the additional parameters are the extent of the outer zone together with its mobility and diffusivity ratios to those of the SRV area. Generate the model. Regression can be run on these parameters to find a better match. But in this case, fracture half-length and reservoir permeability are still selected. The suggested workflow is to use these numerical models for history matching of early data as they are fast to simulate and improve. They should not be used for forecasting, as strictly speaking, they only represent the flow regimes observed at the early stages, i.e. in the linear and pseudo-steady states. The well and reservoir parameters found from matching fast models are then transferred into a full explicit well representation in a numerical model. This is more rigorous when running a long-term forecast as, instead of simplifying assumptions, proper boundary conditions are used. Create a copy from SRVB and name it Full Field Model. Go to Numerical and change modeling type to Simple. Double-check that Fast Model with approximation 5% is ticked and generate. Maximize the 3D plot in the Full Field Model tab. The simulated pressure can be played back. The numerical SRVB is running 5 times faster than the full numerical model in this simple case, saving a lot of time running Improve, and for complex models, the speed up can be several orders of magnitude. Other wells can be added for multi-well analysis, well spacing studies, or planning wine rack drilling schemes, when other wells are placed with lateral and vertical offsets and their fractures penetrating different layers. This concludes this video on SRV and trilinear models in unconventional reservoirs.